Hello, this is an Algebra 2 video. It's Chapter 7, Section 8, and this is the last section in the chapter, so you know what that means, test time. And the good news for this lesson is that we're basically going to be applying what we've already learned in the previous lessons. So there's not really anything new for us to discuss today, but more application. So as a summary, I have the two formulas, exponential growth and exponential decay, which, by the way, are pretty much the exact same formula, with the exception that the decay one has a negative in the exponent. You also might recognize this as PERT. Sometimes we have A equals P times e to the RT. They are the same formula. It doesn't really matter which variables people are using. Scientists tend to use these formulas more, or these variables, I should say. They're the same formula with these variables. So we're going to go ahead and do that as well. But just so that you're aware, it's not really anything different. They're just using different variables. Like, for example, instead of the rate, the R, we have a K. But that's just a constant. It represents continuous growth or continuous decay. So let's get to it. So here we have our first example, and it says, the half-life of a radioactive substance is the time it takes for half of the atoms of the substance to disintegrate. The half-life of carbon-14 is 5,730 years. Determine the value of K and the equation of decay for carbon-14. So again, we're talking about decay here, so we're going to use the formula for exponential decay, which is y equals a times e to the negative kt from the previous slide, and we're going to plug in the information that we know. The cool thing about half-life is that you don't actually have to know what the life was. You might be thinking that they didn't give you enough information. It doesn't really matter because you, for example, all we need to know is that if A is the initial amount, then half of A is what remains. For example, if the initial amount was 20, then at the end of the day, half of 20 would be the half-life, or how much of the substance was left. If the initial amount was 100, then it would be 50. If it was, 200, then it would be 100. So it's always half of what it was originally. So what we can do, instead of replacing it with an actual number, we can replace Y with half of A, because at the end they want to know how much time, they want to know the rate of growth after only half of the substance is there. So we only want half of the substance. This is the original amount of the substance. This is my E. Negative K is what I'm trying to solve for. I'm trying to solve for K. And T, we know, is 5,730 years. And so just like that, we're going to solve for K. And what's going to happen here is kind of nice. When you divide by A on both sides, the A's are going to cancel on both sides. So you're going to get 1/2 equals E to the negative 5,730 K. And then you're going to take the log of both sides. So we're going to get ln of 1/2 equals ln of E to the negative 5,730 K. And then we know that the exponent comes out in front. So we're going to jump over here, and we have ln 1/2 equal to negative 5,730 K times ln E. But again, we said in the previous lesson that ln E is the same thing as 1. So all you really get is negative 5,730 K. So we divide by negative 5,730 on both sides, and our K value will be negative. And now we're going to figure out what that is. So I'm going to go to my calculator and do ln of 1/2, and then I'm going to divide that by negative 5,730, and I end up with a positive number. All right. K is approximately, because the log of 1/2 is negative, so negative divided by negative actually makes us a positive. 0. And we've got 4 zeros here, or 4 decimal places, so we got 1, 2, 3, and then 1, 2. Okay, if I round. 1, 2, 1 actually, but there you go. So K is approximately 0.00012 or 1.2 times 10 to the negative fourth power. So that's our K value. And then it says that it also wants the equation of decay. So all we have to do now is plug K back into the original, and then we're good to go. So let's go ahead and do that. Our formula would be y equals a times e to the negative 0.00012t. So there we go. Y equals a times e to the negative 0.00012t. All right, that's our formula, and we're going to actually use that in our next example. But first, your do-it-yourself question is to find the half-life, or to find the K value for the half-life of plutonium-239. All right, so then here we have our next example, and it says a paleontologist examining the bones of a prehistoric animal estimates that they contain 2% as much carbon-14 as they would have contained when the animal was alive. How long ago did the animal live? Well, the formula that we're going to be using is the same formula that did in part A. We already know that the formula is y, let's do this in a different color here, y equals a times e to the negative 0.00012t. This was the formula that we just figured out for carbon-14, which is what we're using to estimate the lifespan of this animal. So it says here that we want to find how long ago the animal lived. So I will tell you that A is the initial amount of carbon-14 in the animal's body, and we want to know the amount that remains after t years, and that's 2%. So what is 2% as a decimal? 0.02. So unlike before, where A is obviously the original amount, a half A is 50% of carbon-14 that remains, but in this case it's 2%. So we're going to get 2% is 0.02A. So this 0.02A represents 2% of the original amount. So again, we're going to come over here, and instead of y, we're going to plug in 0.02A equals a e to the negative, come on pen, see, it likes me. All right, and again, we're going to divide by a on both sides. They cancel on both sides, so we get 0.02 equals e to the negative 0.00012t. Then we want to take the log of both sides. I should probably get this out of here now. So that's going to give us ln of 0.02, and then negative 0.00012t times ln e, because remember that when I take the ln of both sides, I'll put an ln there and an ln there, the exponent's going to come in front, ln e is going to cancel, and now we're going to divide by negative 0.00012. And t is approximately, let's see here, ln of 0.02, and then divide that by negative 0.00012, and we get 32,600.19 or 0.2, but basically 32,600 years. Alrighty, so to answer the question, the animal lived about 32,600 years ago. All right, now part B says, if prior research points to the animal being around 20,000 years old, how much carbon-14 should be in the animal? So again, this is assuming that their prior research was correct. How much carbon-14 should be in the animal? So now we know the time, because we're saying that the animal was 20,000 years. That's hypothetically right. If he was 20,000 years old. That would be our t value. How much carbon-14 should be in the animal? That's basically going to be y. So we're trying to solve for y. So here we go. I'm going to try to squeeze it in here. Y equals, now here's an interesting thing. If the animal is alive, we're expecting there to be 100% of the carbon-14. We said that if the half-life would be when half of it's left, 2% of it left is 0.02. But if the animal is still alive, we're assuming that he's going to be 100% there. So when you have 100% of the original amount, we're going to use a 1 to represent the original amount because that's going to represent 100%. So instead of A, we're going to put 1, and then E, and the negative 0.00012, and for the time, for the year, we're going to put 20,000. All right, and then we're going to go to the L calculadora. So 20,000 multiplied by negative 0.00012 is going to give us negative 2.4. So we have e to the negative 2.4, and then I'm going to use my calculator again. E to the negative 2.4 power is approximately 0.0907, and if you write that as a percent, it would basically be 9%, because 0.09 is basically 9%. So if the animal was 20,000 years old, there should have been only 9%, or there should have been at least 9% carbon-14 left in the animal, and clearly there was only 2% left, which is why he's actually much older than the 20,000 years. It's actually 32,600 years. So there you go. That is example 2. And so now you're going to do this do-it-yourself question, and then we're going to move on to example 3. All right, example 3 is basically growth here. We're talking about population growth. So it says in 2007, the population of the state of Georgia was 9.36 million people. In 2000, it was 8.18 million people. Determine the value of K, Georgia's relative rate of growth. Well, we know the initial amount was in 2000 because 2000 came before 2007. So the initial amount is 8.18. So for our A value, we're going to put 8.18. And then we know that in 2007, that means that 7 years have elapsed. So for our T, we're going to be using 7. And we don't know what K is. That's what we're trying to figure out, determine the value of K. So K times 7. And this is population growth, so we're not going to have a negative in this case. We have positive K. And then we know that after 7 years, there were 9.36 million. So we'll put that over here, 9.36 million. And we're solving for K. So we divide by 8.18 on both sides. And 9.36 divided by 8.18 is actually approximately 1.14, and equal to e to the 7k. So then we take the log of both sides, ln, and what's going to happen is you're going to get 7k times ln e, and then ln equals ln of 1.14. All right, but of course ln e cancels, and so you get 7k equals ln 1.14. Divide both sides by 7. So our k value is the natural log of 1.14, and then divide that by 7, and we get 0.019 or 0.02. So let's just leave it at 0.019. When will Georgia's population reach 12 million people? So in that case, we basically want to equate it to 12 million. We want the y value to equal 12 million. We're going to use our initial amount here, 8.18. E, we know what k is now. K is 0.019 t. All right, and we're solving for t. So this time we're going to divide by 8.18 again. And we get 12 divided by 8.18 is roughly 1.467. And e to the 0.019t. We take the log of both sides. And by now I think that we're pretty comfortable with the fact that the ln e is going to cancel. So we're just going to get 0.019t on this side equal to the ln of 1.467, and we'll divide that by 0.019. And we get that t is approximately, let's see here, ln of my answer there, and then divide that by 0.019, and we get 19.91, or basically 20 years. When will Georgia's population reach 12 million people? Roughly in about 20 years. And if we're basing this on an initial time of the year 2000, 20 years later would be 2020. So to answer the question here, in the year 2020. Awesome. All right. I think there's a part C. So here we go. Part C says Michigan's population in 2000 was 9.9 million and can be modeled by y equals 9.9 e to the 0.0028 t. Determine when Georgia's population will surpass Michigan's. So we actually need to have both formulas now. And we want to start with Georgia. We want Georgia to surpass, which means we want Georgia to be greater than Michigan. Okay, so basically we're saying that we want to know when will Georgia be greater than Michigan. So all we have to do here is plug in the formulas. For Michigan, we have 9.9 e to the 0.0028 t on this side. And on the left, we're going to use Georgia's, which was 8.18 e. I'm forgetting already. It was 8.18 e to the 0.019 t. All right, that's what we had for Georgia. And we want that to be greater than the Michigan. So now all we have to do is basically solve. So what you want to do in both of these cases is you want the t's to be on the same side. But in order to get the t's on the same side, we have to get the t's out of the exponent. And to do that, we need to take a log of both sides. So we're going to do ln. So over here you're going to get 0.019 t Hold on. I'm not sure that's what I want to do, but I think I will. Yes. The problem here is, sorry, my bad. That is what I want to do, but we have an issue real quick, but we'll address it right now. So what you have here is that you have the ln of a product, 8.18 times e to the whatever. So remember that when you have a product, you have to split it into addition. So I'm going to end up with actually ln of 8.18 plus 0.019 t. All right? Now I'm kind of feeling like you're not following that on this side. So what I'm going to do is on the other side, I'm actually going to do it out the long way so you can see what I'm talking about. So again, this is a product, so we're going to do addition. So ln of 9.9 plus ln of e to the 0.0028 t. But we've already done before that when you have the ln of e to a power, the power is going to come out in front. So this is going to be plus 0.0028t times ln e. And again, the ln e is going to cancel, and all you're going to have is the 0.0028t, which is why on this side I just wrote 0.019t, because the same thing is going to happen on this side. So now, to conserve space, I'm going to go back and write just the 0.0028t up here, and then continue. All right, so I hope that made sense for you. So now what we want to do is we want to combine our t's and put our, remember that the ln of 8.18 is just a number, so even though that might scare you, all we want to do is move it to the other side so that you can join it with this number. And we want the t to come over here with this t. So we're going to subtract 0.0028t, subtract 0.0028t, and then that's going to give us ln of 8.18 on this side, and then we're going to see here 0.01925 minus 0.0028 is 0.01645t greater than, these are obviously going to cancel, so ln 9.9. So now we want to move this ln 8.18 to the other side minus ln 8.18 on this side. So you're only going to have 0.01645t greater than ln 9.9 minus ln 8.18. Notice that I'm not going to put that into the calculator to the very end because I want the most exact answer. And so I would divide by 0.01645 on both sides, 0.01645. And that's going to give me that t should be larger than. So now I'm going to go ln 9.9, and then I'm going to subtract ln 8.18. I'm going to get a result, and then I'm going to divide that result by 0.01645, and that gives me 11.601, or basically 11.6. So as long as the question was, when will Georgia's population surpass Michigan? When t is larger than 11.6, so basically around 12 years. So in 2012. In 2012, we can expect that Georgia's population will surpass Michigan's. Lovely. So now you have this do-it-yourself question, and in the interest of being able to solve the problem later in class, this is part A, and then you have a part B right here, and then we have our last concept for this lesson, our last example as well. And this is a logistic growth model. And basically, you can kind of see elements of the exponential growth model here. But what's interesting about the exponential growth model is that if you were to ask the question about Georgia's population, if you were to graph an exponential model, it's going to look something like this, which indicates that it's going to grow without bound. And if I were to ask you if Georgia's population was going to grow forever, I'm pretty confident that you're going to understand that that's not the case. Populations don't just grow indefinitely; they tend to taper off. And so the logistic growth model, growth model, actually has more of a shape like this, and it kind of tapers off. So it's a better model for population. And so anyway, this is the model of what it looks like. The C value is pretty much the asymptote, because logistic growth models have an asymptote, like an imaginary barrier where the graph will taper off. And so we're going to be graphing those on the calculator. So just be mindful that when you do get to the point of graphing on the calculator, you need to make sure that this whole portion is in parentheses on the bottom of the division bar there. So here is our last example, and primarily being done on the calculator. So I'm not going to graph it on the board, at least not in detail, but I will be putting it in my calculator. All right, so the population of Phoenix, Arizona in millions can be modeled by the logistic function f of t equals, and that's 2.0666 divided by 1 plus 1.66 times e to the negative 0.048 x, or t. Alrighty. And then it says that it wants us to, where t is a number of years after 1980. So that means that year 1 would be 1981. All right, so part A says graph the function for x values or t values between 0 and 500. So in your window, you're going to want to go from 0 to 500. And you're probably going to want to go by 25s on their scale. And then as far as your y-axis, you might want to start at 0 and then go up to only about 3. Trust me on that one. So y min 0, I'm only going to go up to about 3, and I'm going to go by 0.1 on my scale. So every 10th, I'm going to have, 0.1, 0.2, 0.3, 0.4, all the way to 2, or all the way to 3. So graph. So when you do that, if you follow what I said, you should get a graph that pretty much looks kind of like this. All right? Again, I'm not going to graph it all crazy like, because you could use your calculator for that. And if you follow what I said here, your x-axis from 0 to 500 and your y-axis from 0 to 3, you'll see that kind of a graph. So that's part A, is to graph it. Part B says, what is the horizontal asymptote? So they want to know what that imaginary line is right about there. And I said earlier that that actually comes from the formula itself, and it's 2.0666, this value up on top. And if you look at your graph, you will notice that it is in fact accurate. So it's going to be y equals 2.0666 is our horizontal asymptote. And part C kind of refers to part B. It says, will the population of Phoenix increase indefinitely? If not, what will be their maximum population? And that's basically consistent with part B, because we just said that earlier. No, it will not increase indefinitely. The idea here is that it's going to taper off, and that asymptote is like a barrier. It's never going to go beyond that barrier. So when it asks what will be their maximum population is going to be 2.0666 million people. All right. And then it says, I should probably put million. It's not 2.06 people. It's 2.0666 million people is going to be the maximum population. And then the last part says, according to the function, when will the population of Phoenix reach 1.8 million? So somewhere along on your y-axis, there is a 1.8. And we would like to know what t value is that. So we're going to do that on the calculator. You could actually do it algebraically and put 1.8 in the y value over here and then solve the equation algebraically. But you can do it on your calculator a lot easier and a lot faster. And so what I want you to do is go to y2 on your calculator. We already put in y1 this equation. In y2, I want you to type in just simply y equals 1.8. And when you graph that, you are going to get, you're going to get a line, a horizontal line that is going to go straight across like that on your graph. And so what we want to do now is use the calculator's features to find the intersection of the line and the curve, and that will be your t value. So we're going to go second, and we're going to go trace, because that's the calc feature. You're going to go to option number 5, which is intersection. And then it's going to ask you what the first curve is. And as long as the cursor is blinking on on this curve, it's got like a little blinker going on, you hit enter to say yes, that's the first curve. And then it should bounce to the other equation, and the cursor should now be blinking on the line. And you hit enter again. So you're going to hit enter twice. And then it says